And he will talk about beyond integrants, positive geometry of scattering amplitudes, part 1 and part 2. Thanks.
All right. I'd like to thank all the organizers, both for very generously giving me so much time, as well as really putting together. I know we've all joked about it, but it's really been a really fantastic meeting so far. It's been a tremendous pleasure to participate and hear so many interesting talks. So I will be talking today on work that's largely been going on with the Surfacehedra crew. Really have to say one of the real pleasures of the pandemic has been working actively with these guys, Hadley Frost and Giulio Salvatore, and Pierre-Guy Plamondon and Hugh Thomas, as well as some discussions that we've had about these things also with Sebastian Mizera and Aaron Hillman. And indeed, we've been talking for a number of years about the connection between positive geometries and the rational forms associated with scattering amplitudes via the sort of idea of the canonical form associated with positive geometry. But something that's deeply related to this question of finding the canonical form has always struck me as also giving potentially a direct conduit to getting the actual amplitude. So I want to say a little bit about this to begin with. And this sort of fantasy was a big part of the reason for starting to think about these Surfacehedra, starting to think about the trace phi cube theory, I mean, to begin with a number of years ago, because it seemed easier to realize this fantasy in this setting to begin with than in n=4 super Yang-Mills. But anyway, that's what I want to tell you about today is two quite different aspects of the sort of journey towards the actual amplitude. First, in the context of trace phi cube theory, where we'll see how the positive geometry associated with the Surfacehedra suggests two different representations, sort of integral representations. I would say roughly Schwinger parameter-like, but definitely not Schwinger parameter, something that combines all the diagrams together, the whole amplitude into a single object, and presents the actual amplitude as an integral over the positive geometries. One of them is very much related to the picture that we've been talking about for many years of the dual amplituhedron, this mythical beast that I'll say a little bit more about. The other one is more closely related to stringy canonical forms and stringy amplitudes. And I'm actually putting this talk one together about trace phi cube theory. I realize that there's really a lot of stuff here. I'm not going to be able to, in one talk, cover both of these things. So in this talk, I will talk mostly about these stringy amplitudes associated with the binary realization of Surfacehedra in the cases that they're available to us. One reason I'm talking about them is I think they're more new, and I'm especially excited about them because at the very least, they give us some alpha prime regulated version of the field theory amplitude. So they, of course, regulate ultraviolet divergences. This is trace phi cube theory in any number of dimensions. It's not n=4 super Yang-Mills. So if you integrate, there'd be UV divergences and so on. But it really appears like even at finite alpha prime and even at loop level, and I'll talk about what happens at one loop, that these amplitudes, while they don't look on the face of it at all similar to the much more complicated expressions for string amplitudes at one loop, they really look really stringy. And they certainly look like some new UV complete kind of exponentially soft at high energies in the physical region. All the stuff that we get excited about with string theory seems to be a feature of these stringy amplitudes as well. So it's clearly somehow connected to a string theory, although we don't know how exactly. Is it a new kind of string theory? Is it just some standard way of thinking about the string integrals in disguise? I will tell you various aspects about this that we don't understand very much about it. But anyway, that's the reason for me focusing on this the string amplitudes in this talk, because I think it has the most amount of novelty, and it might even be associated with some new physical sort of models that would be, I think, fascinating to understand better. In the discussion session later today, I mean, there's all sorts of things that we could talk about. If people want to hear about the dual Surfacehedra, which is a quite different representation, again, of amplitudes as integrals over the duals of these Surfacehedran polytopes that Giulio was talking about, then I would be happy to say a little bit about it there, but there are many other subjects that we could talk about there as well. Okay, so that's the plan for lecture 1. And my plan in lecture 2 is to go back to the amplituhedron, the n equals 4 superangular amplituhedron, and talk about how the geometry of the amplituhedron, already for the case of 4 particle scattering, suggests a different organization of different way of thinking about the amplitude, not as a sum over sort of a single positive geometry, but as a sum over a large number of what you can think of negative geometries. And there's a very simple sort of combinatorial picture associated with that, that rather remarkably to me allows us to deform the amplitude with some natural parameter. As we, so we're not talking about the exact amplitude, we're talking about a fraction of the negative geometries that are associated with the problem. But that fraction can be, that set can be summed to infinite order and get some expressions that make sense at arbitrary finite coupling constant, so that we can get some approach to going to extract non-perturbative physics. What's interesting about it, and what we'll talk about in the next talk, is that the objects that we run into as we extrapolate them to strong coupling have all the qualitative features that we've seen for the strong weak coupling from gluons to empty de Sitter space that we've seen in the cusp anomalous dimension and various other quantities that are known non-perturbatively. But we're going to see all those phenomenon with no heavy machinery, essentially doing nothing other than a little bit of the combinatorics of the amplituhedron and a tiny frisson of differential equations that allows us to go to a strong coupling. So the second talk will be all about the n equals 4 superangular amplituhedron and the sort of journey towards strong coupling and discovering how empty de Sitter space comes out of these positive geometries. This talk will be about trace phi cube theory and Surfacehedra. Okay, so a quick reminder of the story that Giulio summarized. So Surfacehedra are polytopes that are associated with any two-dimensional surface. And as he explained, these are polytopes that capture the combinatorics of non-crossing arcs on this surface. So there's a facet of this polytope associated with every homotopy equivalence class of arcs. In general, for the simplest situations, these polytopes are finite, but soon you can get curves that wrap around the surface infinitely many times. So these are infinite polytopes. They have an infinite number of facets, and they have a kind of a fractal structure. As Giulio was emphasizing in the first versions of the talks and of our work, never mind the talks on this subject that we started talking about last summer and even in December, we were always imagining making these objects finite by doing some kind of external cutoff on the arcs that we're talking about. And that was a kind of a necessary thing to do. In a sense, it's like trying to get to the continuum of a field theory by first learning what happens on the lattice and then understanding how you carefully have to take the continuum limit for the thing that you want to emerge. But it does look like there is a naturally infinite object that has to be defined with a little bit of care. A little bit of magic has to happen for the infinite object to make sense as a polytope. But in all the examples we've looked at, and conjecturally in all examples, that magic does happen. So there's an infinite polytope associated with the generic surface, and the facets reflect the combinatorics of crossing surfaces, and in particular, the facets have a factorizing structure or a pinching structure that exactly reflects the cutting and pinching of the corresponding arcs on the surface. Especially interesting are the existence of new kinds of new kinds of curves, which are closed loops on the surface, these things that we call delta, where the pinching of those arcs corresponds to a pinching of surfaces like this. And this gives a very interesting sort of entangled product of the polytopes on the two sides, with the entangling as explained by Giulio, taking care of the fact that any arcs that wind around this side on one side have to end up winding around in the same sense coming out the other end. These closed loops, as has been said a few times, have many of the features that you would associate with quote unquote gravity, and they're forced on us. There is no way we could talk about these polytopes naturally without thinking about it. Okay, so, oops, I don't know what happened. Sorry, guys. Okay, so, okay, so I don't know why I'm having this difficulty. Okay, so now, that's what they are as a positive geometry. So the surfaces, but the canonical forms associated with these positive geometries are the natural infinite notion of integrand that Giulio referred to in his talk that you would associate with the trace phi cubed theory at all loop order and beyond the planar limit as well. So these are some pictures that would be associated with trees, one loop. We'll talk about these things in a detail, how to think about them. The three punctured sphere, the annulus, the torus with a puncture, and these are the sort of classes of Feynman diagrams, ribbon diagrams, fat graphs that you'd associate with them. So here already we see some of the pictures Giulio talked about, these fascinating infinite polytopes, but they are the amplituhedra that would be associated with the trace phi cube theory, with the contributions associated with diagrams with these topologies as shown in this example. All right. And of course, an open issue, a question in this business is, how do you think about this infinite covering of the infinitely many times the same diagrams occur over and over again? And again, as Giulio said in his talk, there's various ways of thinking about it. You can think in terms of shutting off some of the faces of this polytope so that you cover all the Feynman diagrams once or twice or any number of times you want. In all the examples we've seen, there's a natural way of doing that. So it's not even that you have to sort of manually say, I want this diagram and that diagram. It's a natural way of shutting off the facets to make these polytopes finite, which again was the way we were running into them to begin with. But we've seen over and over in this business that you should let the natural things do what they want to do. And here, the infinite object seems to be the natural thing. And so we should try to, I think, find other ways of thinking about the infinity associated with the integrand. And as we'll see, there's one way that's being suggested naturally from these stringy amplitudes that I'll be telling you about. But anyway, going back to a very general part of this whole program, we have these positive geometries and they're associated with canonical forms. The canonical forms are what connected to a physics. But for a general curvy positive geometry like the amplituhedron, the very big open question in this business for a long time has been, is there some invariant intrinsic way of computing this canonical form? The one way we know of is to learn how to triangulate the surface and add up the canonical forms with the little pieces when they're simple, but that's not very satisfying, obviously. And you'd like to have some intrinsic way of defining canonical forms, some intrinsic way of even making clear that such a thing exists. And we don't have that in general. And I think that's probably the biggest open problem about this whole subject, especially when it comes to the n=4 super Yang-Mills amplituhedron. But in the particular case where P is a polytope, we've known for years and years about one beautiful characterization of the canonical forms, and a little more recently, there's another one. These are totally intrinsic things. One of them is that the canonical form is essentially the volume of the dual of the polytope. So if we have the canonical form, the polytope lives in some projective space Y, the canonical form thought of as a form on Y space is this universal form on the projective space Y, D, and Y, multiplied by the volume of the dual of the polytope, where in the dual, Y is taken to be the hyperplane at infinity that defines the space in which the affine space in which the polytope lives. Okay, and so this is the concrete formula for the volume. Okay, so this is a beautiful intrinsic formula. It makes no reference to triangulation or anything like that. And starting from this formula, you can actually see that this object indeed has logarithmic singularities on all the boundaries of the polytope. Another formula that actually produces a form that is deformed by parameter alpha prime to begin with is this one, okay, where we integrate in order to find the canonical form on some space X. And in general, a polytope that is presented as the Minkowski sum of a bunch of pieces, that could just be one of them, but it could also naturally be Minkowski sum of a bunch of pieces, then it's given by this stringy canonical form, sorry, the factor of alpha prime to the n that was supposed to be in front of this whole thing. Okay, and this is a second description. If you give me a representation of the polytope as a Minkowski sum, this very naturally gives you a canonical form that now has a parameter alpha prime associated with it. And as alpha prime goes to 0, it returns the ordinary canonical form, but it gives you something interesting at finite alpha prime as well. Now, it would be wonderful to find analogs for general positive geometries of these two pictures. Especially for the loop n equals 4 amplitude, as I said. There's lots of circumstantial evidence that this mythical dual amplitude should exist. There's no clue yet whether there's an analog of stringy canonical forms for the n equals 4 amplitude, but it would be wonderful if these things existed. But I should say that, you see, I've stressed the motivation here is about finding an intrinsic representation of the canonical form. We're still caring about integrands and canonical forms, no mention of amplitudes yet. I mean, purely within the world of positive geometries and integrands, we want to find these kind of intrinsic representations of the form. But one of the motivations is that if we had such a representation, it should directly give us the amplitude. And at least that's a sort of dream. And the reason is that dual amplituhedra, even dual polytopes, are really some souped up version of Feynman parametrization. So let me try to explain what I mean by that. When we begin, teaching how to do loop integrals, and we hand someone a loop integral that looks like this looks hard. Okay, so we don't know how to do this loop integral. But following Schwinger, we Schwinger parameterize all of these, all of the propagators. So in general, we can do it with any denominators d. We write them in this exponential form. Now in this form, we could follow Feynman and do one of the integrals over the overall scale of all of this to turn it into an integral over a projective simplex. Okay, so this is the Feynman form. This is the Schwinger form. They're essentially identical, of course. But now in this form, we can do the loop integrals. Of course, that's what we all know. That's what we teach. In this form, we can just do the loop integral by completing the square, which is equivalent to doing the Gaussian integral on the exponential Schwinger representation. And, if we don't have any numerators, we get some expression like this. We have with that expression, if we have numerators, we can just differentiate with respect to some of these alphas. And this basic object F we get from, at one loop, for example, we get from completing the square. And okay, that's the standard thing. We're now no more loops up here because we integrated them out. We just get dependence on kinematic variables like this. Now, this formula, the Schwinger parameterization or Feynman parameterization formula is nothing but the formula for the volume of a projective simplex. Okay, so so if you ask for the volume of a simplex in a projective space whose vertices are W1 through Wn and Y is the hyperplane at infinity, then this is the formula for the volume. This is most familiar from junior high school. If you put Y to infinity like 1, 0, 0, 0, 0, then this is just the determinant. Okay, but in general, projectively, there are these Y's downstairs to make the weights work out right. And that's the volume. And this is it represented manifestly as a volume. Okay, so when W is inside the hull, the integral over W inside of the hull of these W1 through Wn of 1 over W dot Y to the n. And from the point of view of loop integration, the crucial thing about this is while the left-hand side has a quote unquote complicated dependence on Y, the right-hand side has a very simple dependence on Y, just this power of 1 over W dot Y to the n. And so again, the hope was that there's something like this happening in n equals 4 super Yang mills. For example, you might hope even at one loop that when we talk about the canonical form for the loop amplituhedron, which is now a function of lines AB in momentum twistor space, that there's some kind of representation for it, just like there's a representation for the form of a polytope, where we integrate over some space, but where the dependence on y is really simple, just as w dot y to the n plus 1, that we'd have something like that for the amplituhedron, where the dependence on AB would be really simple. And now everything here is in quotations. I don't know exactly what this means, some kind of integral over some kind of dual space. But the whole point is that the dependence on AB here should be really simple, so that then A, this would be an intrinsic representation of the canonical form, but B, you could then do the integral over AB and just get this expression, okay? And of course, this would be wonderful because then nothing would be wasted from the positive geometry of the integrand. In fact, by finding the most intrinsic representation of the positive geometry of the integrand, that would also give you the amplitude, or at least loop order by loop order would give you the amplitude. So it's obvious why this is an attractive thing to hope for. And in fact, you know, we've tried for many years, as I said, this is kind of a mythical object, the dual amplituhedron. We tried to sort of find it directly, and without much success, other than gathering more evidence that it exists. But this dream was, at least for me, a big motivation to take a detour from n equals 4 super Yang-Mills into this scalar theory, this trace phi cube theory. At least when it became clear there was some connection to geometry through the Surfacehedra and so on. Because then now the amplituhedra would just be polytopes. And so if we could find the polytopes, we know what duals of polytopes are. And so the hope was that this whole picture of the dual of the amplituhedron would make sense for the positive geometries of this trace phi cube theory. And as I mentioned right at the beginning, we can now really precisely realize this dual Surfacehedron picture for amplitudes. So for instance, the full one loop amplitude is a single integral over a simplex. And that simplex is determined by a mapping into not the Surfacehedron, but the dual of the Surfacehedron. It's a completely known map at one loop. And I mean, it's just a matter of working to do it at two loops, or but the sort of program for doing it is clear. So as I said, this is something I'd be happy to talk about in the discussion session, but I won't say more about it here. Because meanwhile, we also learned about stringy canonical forms, and I just want to emphasize that stringy canonical forms, if we could realize, if we could associate stringy canonical forms naturally with our with the Surfacehedron geometries, that would also allow us to perform the loop integration. And why is that? Because it's, again, just like in Schwinger parameterization. You know, the kind of the natural and beautiful way that we could hope that this would arise is through these binary geometry realizations of the polytopes. So there we have some integral that looks like this over some variables and some polynomials raised to powers, but all of the dependence on kinematical data is in these powers. So some of these kinematical data is just external Mandelstams, but some of them will involve the loop variables. And again, let's say you're at one loop. Some of these x's will look like some L plus p squared. But the point is that all the dependence on the loop variable is just exponential, like, you know, e to the something L squared. And therefore, we can do all the loop integrals as Gaussian integrals, just like we could do with Schwinger parameterization, leaving you with some integral over this binary realization of the positive geometry with some more interesting integrand that comes from doing the Gaussian integral. And that would then give you a representation of the actual amplitude as an integral over this binary geometry. All right. So I'm going to talk about that now, and we're going to focus today on one loop. There's a lot of new things going on, so we're going to focus on one loop, but both the planar and the non-planar example of one loop diagram. So for the single trace things, where these are just normal planar one loop diagrams, as well as double trace things at one loop where they're non-planar. And here I'll really focus on this very simplest example of this double trace bubble, where the corresponding surface is the annulus with two marked points. And the main reason I want to talk about this example is that this is also the first example where we encounter this infinite integrand issue that was brought up in Giulio's talk. We'll encounter it, and then we'll see how this stringy integral and the stringy amplitude associated with these things naturally solves the problem and gives us directly an amplitude, no extra infinity, just directly what we want. All right. So let's first talk about these the usual planar guys. And so what I want to do now is step back for a second and tell you exactly what these polytopes are and the simplest way of thinking about them. So in Giulio's talk, he talked about various ways of understanding these, or at least characterizing these surfacehedra in generality, but it's still sort of conjectural how we have to find the constants associated with these interesting, with the Skene relations he talked about, or the distances associated with hyperbolic geometry he had talked about. Instead, what I'm going to do here in these really simple examples of this thing that we're now calling d hat n, the reason for the hat will become clear in a second, there's a totally explicit characterization, which in fact is, I think, amazingly simple and beautiful and essentially identical in conception to the way we think about the ordinary tree-level isosahedron, especially from the sort of space-time wave equation picture. So if you couldn't follow any of the sort of abstract discussion in Giulio's talk, or if you've been even asleep for the past 20 minutes, this is probably the most interesting self-contained 10-15 minutes of the talk that it would be worth waking up for. Okay? So first, let me tell you what this d hat n is, which is really a matter of telling you what the arcs are on the surface that we're going to consider. Okay, so here's the example of d hat 4, here are some examples of arcs. So here's an arc which I've drawn so that it's spiraling around one way, and this is what we'll call y1 plus. There's another arc that spirals around the other way that we're going to call y1 minus. That's a kind of funny thing from the perspective of Feynman diagrams. Each one of these arcs just corresponds to one of these sort of loop propagators in the dual fat graph or ribbon graph. But from the perspective of the surface, we really have to have two copies of them. And this two copies is really a remnant at one loop of the existence of this infinite mapping class group that Giulio described in his talk in general. So it's the kind of first hint of this infinity to come. Here it's just the little Z2, but from the perspective of the surface, it's not natural. And when you draw this arc, you really have to think about it, as Giulio described, as a laminate, and it's natural to think about either spiraling one way around or spiraling the other way around. And in the language of cluster algebras, these would be, tagged and untagged variables. Okay, but anyway, so there's two of these kinds, y plus and y minus. Okay, then we have this arc. We also have that arc. So the arcs aren't just labeled by I and j. We say that xij is such that that j is always to the right of I. Sorry, that the puncture is always to the right of the chord ij. So x13 and x31 are separate arcs. X41 would be a boundary arc here. But we also then allow x14, and we will also allow these self loops, so what you could call x11. Okay, so we have all of these guys. It's important to have all of these guys for a variety of reasons that I'll talk about in a second. But right here, I'll say that this is where there's a difference from the standard cluster algebra way of thinking about things, where you would not, for example, talk about these guys. Okay, you would still have the tagged and the untagged variables, but you'd not talk about these guys. Anyway, here's some examples of what these arcs look like as propagators in Feynman diagrams. For this triangulation of the surface, it's just a box, and so this purple arc here is that propagator. These guys, which go around the puncture but which are adjacent to each other, correspond to bubbles. This bubble the propagator corresponding to a bubble on an external leg. The reason why we have 3, 1 and 1, 3 is that in a diagram like this, 3, 1 would correspond to the propagator on one side, and 1, 3 corresponds to the propagator on the other side. And I think, as Julia mentioned in his talk, it's very important from the perspective of canonical forms that these are not identified, because otherwise we'd get a double pole. Whereas here we're giving them different names, so in the canonical form there's no double pole. And finally, you see these bubble guys are the propagators associated with tadpoles. Okay, so these self loops here are bubbles associated with tadpoles. All right, so let's see again then, what are all of the diagrams that we would draw for D2 hat, what we call D2 hat. Okay, so we'd start with this triangulation, which is again dual to a bubble. And we could mutate this propagator to go to this one. I didn't draw the Feynman diagrams here, but this one would be a tadpole coming out in this direction, the way I was just drawing with my hand there. And then now I can flip this plus spiraling guy to the minus spiraling guy and go around the same way. Okay, so the sort of combinatorics here is that of a hexagon. Whereas in the standard cluster way of thinking about things, where this would be D2, it's different. You never see these self loops, and instead you allow the plus and the minus tagged and untagged guys that emanate from the same vertex to be compatible with each other. Okay, so this is the picture you'd have for D2. You see, in this picture, this middle guy here is like squashing together these two guys. If I take these two guys, put them on top of each other and throw out the bubble, this is what I would get. And this is, of course, natural from any point of view. It's natural from the cluster algebraic point of view, but it is unnatural from our point of view. Okay, and it's very unnatural to make these plus and minus arcs compatible with each other. They correspond to things that are spiraling around a huge number of times one way and a huge number of times the other way. So these things are intersecting like crazy. And so it's really sort of wrong to say that they're compatible with each other. Another headache that was associated with them that really sort of stopped us doing some of the things that I'm going to be telling you to do already like a year and a half ago when we first, 2 years ago when we ran into the DN polytopes, is that these don't have a natural diagrammatic interpretation, these things. You see, you want to associate this with a tadpole diagram, but these plus and minus variables are doing double duty. In those diagrams, they're being interpreted as a tadpole propagator, whereas in other diagrams, they want to be interpreted as ordinary propagators. Okay? So they don't have a good diagrammatic interpretation. Whereas on this side, everything is natural from the perspective of the surface, as well as the diagrams and factorization and the connection to physics. Okay? And okay, this is another example. I think Julia showed this in his talk. Again, these D3 hat polytopes are sort of opened up to precisely not let the tagged and the untagged guys touch each other. And introducing these new tadpole variables precisely lets us do that. All right, but now I want to tell you what I think is an extremely simple and lovely picture for how to think about the polytopes at tree level and at one loop. Okay, so there's the tree polytopes for n+3 point scattering, which are the A and Surfacehedron, and the polytope for one loop scattering at n points, which is this D hat n Surfacehedron, this D hat n polytope. And I'm going to do it from the perspective of the wave equation that we've talked about before in the context of the Surfacehedron, but it's going to even be a slightly different point of view than we had before. And from this new point of view, as you'll see, there's a totally uniform way of talking about these two cases. So let's go back to think about the wave equation in 1+1 dimensions. So it's du dv x equals 0. We'll come back to add sources in a moment. I know, of course, the point is that here the solution is a left mover and a right mover, a y plus of u and a y minus of v. And these are the two functional, two functions you need to provide initial conditions to determine the solution of the wave equation. Okay, so I have to give you a y plus and a y minus function of a single variable worth of initial condition information in order to determine the solution. So a natural question is, what are nice ways of just presenting this initial data? How should I present to you this initial data of the y plus of u and the y minus of v? And maybe the first way you think of it from this point of view is that, well, just give me a U line and a V line, and just give me Y plus on the U line and Y minus on the V line. So that's the first thing that you might do. Okay, so here's the picture. I'm just going to draw a line like this. On this line, I'll give you, on this 45-degree line, I'll give you Y plus. On that 45-degree line, I'll give you Y minus. Of course, I had better agree on that tip. And then from that initial data, I'm going to solve for X everywhere else, just from X is equal to Y plus of U plus Y minus of V. And now I'll add the possibility of a source. So if I have some source C, I'm going to write that X is Y plus Y minus the integral of this source over the obvious square associated with this picture. All right. So this is maybe the first thing that you would try to do if you just wanted to sort of present the initial data in a nice way. Of course, if you wanted to, let's say, only give Y plus, well, you have to give the other data somehow. Okay, so what you can do is impose another boundary condition. So you can take this whole picture and just chop it off somewhere and say, let's say on this line that X equals 0, and we can even correlate this X equals 0, let's say with the value there, although it doesn't really matter that much. But anyway, let's just say that we put X equals 0 here and there. And so now what that does is it puts a constraint between Y plus and Y minus, okay? Because X has got to vanish here, I learned that Y plus Y minus the integral of the source inside this yellow region has got to equal 0. So this relates Y plus and Y minus, and therefore I can give you Y plus as free data, and then Y minus is determined, or Y minus is free data and Y plus is determined. Or I could just give you this picture where I say I have Y plus, Y minus, as well as a constraint that X equals 0 there. Okay, so that's the first way you might imagine presenting initial data. And then once you do that, you can discretize the surface the initial data is given on and shoot out light rays, and in that way discretely cover the whole space. So for instance, if I do that in this picture and I discretize down here or up there, it doesn't matter, and I shoot out light rays, and I fill out the rest of the region with a grid. And of course, this looks very, very familiar from the sort of wave equation picture for the ABHY Surfacehedron. But I want to stress a little difference in attitude here. We're not saying that these, here what I'm saying is that I'm going to directly define X here as Y, as the value there, plus the value there, plus the sum of these meshes. That's my sort of fundamental solution of the wave equation. And from that, now I just ask that all these X's are positive, and that cuts out the ABHY Surfacehedra. The fact that with this definition, it turns out that X plus X minus X minus X is equal to one of these little meshes is a derivative fact. I mean, of course, you could start from that fact too and work backwards to see that you get the solution of the wave equation. But the point of view that I want to pursue here is that we just give the solution of the wave equation first, and everything else follows from that. And in particular, I don't have to tell you this. All I have to tell you is that I have these constants here. I arrange that the X is equal to 0 there, that puts some constraint between the initial values here and there. And then I just ask for all the X's inside that are determined by the wave equation to stay positive, and that cuts out the ABHY Surfacehedra. All right. Well, what's something else that you could do? Another thing that you can do that's in many ways even more obvious. It's even more obvious in the sense that it's what we teach kids to do when they first learn to solve the wave equation. You know, normally when you solve the when you first see the wave equation, you're thinking about evolution in time and space. So it's a second order equation in time, and like a good Newtonian person, you say I should give you the initial value of X and the initial value of the time derivative X dot. So I have to give you the data on a spatial surface of two things, X and X dot, and then I evolve and I solve for X everywhere inside. Okay, it's because we are slightly fancy that we know that the good variables are U and V, that this second sort of more null picture was natural to begin with. But really the very dumbest thing you might do is just to say, give me the initial data on this spatial surface. So on the surface at any given point, I'm going to just give you Y plus of X and Y minus of X on that spatial slice. So this one point here has 2 degrees of freedom on it, just like we're used to, x and x dot, okay, or at that point. And then I'm going to solve the wave equation everywhere else in exactly the same way, except that here, because I'm giving you two things, a plus and a minus, I'm making a little choice that the x here is going to be the y plus on the left plus the y minus on the right. And then, but the rest is exactly the same. So x is y plus y minus the integral of the mesh constants in here. Once again, just like before, I can impose a condition somewhere far away. So here I can impose that x equals 0 on another spatial slice, which lets me relate the y plus and the y minus to each other. Again, just exactly the same as in the previous picture. And then we'll dismortize and shoot out light rays. Okay, so now we're going to get a picture like this, where up here I've enforced that everything is equal. Again, I have the condition that everything is going to equal 0, and there is a constant, positive constant associated with all of these little meshes in here, including these triangles down here, with the formula that x is y plus left plus y minus right minus the sum of all the sort of charges in those meshes. And now all we have to do is label these guys. And here are the labels. So upstairs there'll be 1, 2, 2, 3, 3, 4, 4, 1, 1, 2. Okay, so those are the boundary components. Then very similarly as in as we're used to seeing in the usual picture for the Surfacehedra, 1, 3, 1, 4. But you see, now there are some special points in this picture. There are the tips of these triangles. They're a little different than the other ones. And in this picture, we keep labeling them. It's 1, 3, 1, 4, 1, 1. Okay, and the rest of the guys on the bottom I already called y's, and there they are. So I've given everybody names here, and as you can plainly see, all the labels here are precisely the labels of dn hat. Okay, not of dn, but of dn hat. And in particular, we have these extra loop variables of 1, 1, 2, 2, 3, 3, and so on 4. And that's it. The ABHY Surfacehedron for dn hat is exactly the same as for an. You just say that all these x's are positive. Now, in this case, it's slightly more interesting. You begin with this as the primitive condition, and you derive from it that there's a bunch of relations that have to be positive. And now there's different kinds of relations. There are things that look like x plus x minus x minus x. There are some things that look like x plus x minus x, and other things that look like x plus x minus 3x's. Okay, and this is the sort of thing that we've seen in the dn cluster polytope. But again, we're not drawing any little Dinkin diagrams or making even small excuses for what's going on at the edges here. We're just being the dumbest possible physicists, solving the wave equation in the stupidest way possible, and it just immediately gives us the dn hat polytope. Not the dn, but the dn hat polytope. Okay. Now, an important feature of these mesh relation sort of wave equation realizations of the Surfacehedron is that it also tells you something. It tells you this is not a random Surfacehedron. It's an Surfacehedron that's naturally produced as a Minkowski sum of a bunch of simple pieces. And what are the simple pieces? It's a very sort of obvious and natural picture. It's the sort of discrete analog of a Green's function. Every one of these little squares is filled with a mesh constant. So you can wonder what happens to the polytope if you shut off all the mesh constants but one of them. And of course, what happens is that the polytope degenerates to something much, much simpler. In this case, all of these things, no matter if you turn on one of them and turn off everyone else, it degenerates to a particular simplex. And then you can realize the whole Surfacehedron as a Minkowski sum of those little simplices weighted by these mesh constants there. Okay. Well, exactly the same is true of dn hat. And so all we need to know is what those Minkowski summands look like. And they're the following beautiful and very simple structure. They're just simplices, okay? And so if I start from this one that's furthest up along this chain, so if I turn on just this constant here and put everyone else as 0, the dn hat polytope degenerates to this simplex, the interval. If I turn on the next one, well, it's a triangle, but y3 less than y4 less than 1. This one is y3 less than y4 less than y1 less than 1. And finally, that little triangle at the end is y3 less than y4 less than y1 less than y2 is 1. So they're just the cyclic intervals. Okay. All of the summands, and if we take the Minkowski sum of all of these cyclic intervals, we get the full dn hat polytope. Because they're simplices, there's a very simple polynomial associated with every one of them, and given a simplex that I can of this sort, where the smallest variable is xi and the biggest variable is xj, and they're standard between 0 and 1, there's the following trivial polynomial whose Newton polytope is that simplex. Okay, just the vertices of that simplex, which is 1 plus the biggest one, yj, plus yj minus 1, plus dot dot all the way yj, the product of all of them. Okay, so that I'm going to use that notation. All right. So summary so far, there's this sort of a second, sort of more Newtonian way of thinking about the wave equation. Discretizing it gives you exactly the variables of the dn hat surface, and we represent the associated ABHY-like polytope with as a Minkowski sum of these simplices. And something else that we've understood is that when this happens, we can look for U variables that realize the corresponding geometry of the polytope in this binary way. And the way you do it is very simple. You just write down this polynomial. So first, there are some variables associated with the boundaries here. These are these. Let's say I made the choices are the y pluses. So you plonk these down, and then you take the product over every little over all the meshes that correspond to the summands in the picture, the corresponding polynomial to the negative its corresponding mesh constant. And you know that each one of these c's is written in terms of the underlying x's, just however you can from the relations implied by this picture. So you just rewrite this expression as a product over all of the actual x variables in that picture of some ux to the power of x. And in this way, there's an explicit expression for the u variables. Again, the like uxij's look sort of similar to the cross ratios that we're used to seeing for the ordinary Surfacehedron, but there's something slightly different in the case where they're adjacent, slightly different for the loop guys, and of course we have these expressions for the tag guys. And very beautifully, these u variables satisfy the u equations for the dn hat surface. So now the equations look like ux plus the product of all the x primes that are incompatible with x of simply the number of intersections of the two curves with each other on the surface, where the intersections are defined so that a tagged and an untagged, or the plus and a minus arcs, they're always incompatible with each other, and they're taken to have intersection number 1. Okay, so here's an example in the D2 hat case, which is that hexagon that I showed you. So here is explicitly what the u variables turn out to be. There's 3 of them here. You shift them over to get the other 3 cyclically, and here are what the u equations look like. So the u for y1. So who is incompatible with y1 plus? Well, y1 minus and y2 minus are incompatible, and so is x22. Okay, so that's the equation for u y1 plus, and you shove this in, you can verify this equation is satisfied. And now we get some more interesting powers for ux11 here. Y2 crosses it, y2 plus, y2 minus crosses it, but also x11 crosses it twice. So there's a power of 2 here. Once again, you can shove these things in here and see that these are satisfied. Okay. So these u variables that come from these very simple summands by the sort of standard machinery for how we get u variables from Minkowski sums give us a representation of the solutions of the u equations associated with this dn hat surface. Again, these are not the u equations associated with the dn polytope that we talked about already before, but of this better thing from the perspective of the surface. All right, so that's all we need now. Now we can finally talk about what the stringy forms are at loop level, and then do the loop integrals and see what we get. So to begin with, let me remind you how things worked at tree level, and why it's especially interesting to have these binary realizations. Okay, so at tree level, we have this representation of a stringy canonical form, where we imagine we parameterize the u variables, now just associated with uij on the surface, maybe in terms of some positive coordinates y. So we just integrate over all the y's, an n minus 3-dimensional integral. Oh, I forgot to put the powers of the y's here. So there's some y to the alpha prime y here. No, sorry, in this form, no, sorry, I apologize. This is perfectly fine. So it's just a product over all the uij's to the alpha prime xij. Okay, that's the stringy canonical form at tree level. And on general ground, it's guaranteed as alpha prime goes to 0 that this will reproduce the canonical form of the isosahedron, of the corresponding ABHY isosahedron. But the reason why the fact that these u's satisfy this binary equation is so important is we learned something interesting. Where do the singularities of this come from? They come when some of the u's go to 0. But when some of the u's go to 0 here, because of these binary equations, the incompatible uys go to 1. And that means that in these powers, all the ones that involve the incompatible variables disappear because all of those u's go to 1, even when alpha prime is finite. And that's the crucial thing, is that omega alpha prime reflects the factorization of the amplitude and the factorization of the surface, even at finite alpha prime. Not just as alpha prime goes to 0, but even at finite alpha prime. And that's a magical thing. And that, of course, in the particular case of the isosahedron, this formula is what we sometimes in this business call the Kobe-Nielsen amplitude. Okay, this does give you what looks like a string amplitude, despite there's no worldsheet CFT, there's none of that stuff, but just from this perspective of binary geometries, we get exactly the same expression. I want to pause here for a second to say, I mean, certainly all the physicists know this, but we call this a Kobe-Nielsen amplitude. Of course, it's not any amplitude that Kobe-Nielsen wrote down. And there's no known string background that literally corresponds to this amplitude. In other words, for trace phi cube theory scalars rather than gluons. The conventional open string, bosonic open string has tachyons, and that doesn't give us this nice form with the Park-Taylor denominator or this D-log form associated with these positive geometries. One small comment I'll make that probably many people have observed is that despite the fact that we don't know a known string background that goes along with this theory, if we just compute the tree amplitude even at 4 points, we know there's an important check we can do on these amplitudes that's quite miraculously satisfied in string theory, that when we think about the poles of the amplitude, the massive poles, they have to have an appropriate positivity property to be interpretable as producing these massive high spin particles with positive probability. And just asking for that to be the case for the 4-particle amplitude in string theory, like the Veneziano amplitude or the Virasoro-Shapiro amplitude or the open string gluon amplitudes, you learn that, for example, the critical dimension, that it will cease to be unitary if the number of dimensions is greater than 10. But in less than or equal to 10 dimensions, it is unitary. And it's a nice fact about this amplitude, which is not the gluon amplitude. In fact, it's related to it just by multiplying by a factor of u, that this is also positive. There's a simple reason why the positivity, the known, somewhat miraculous positivity of the string amplitude, which follows in some quite indirect way from the no-ghost theorem, is actually inherited by this trace phi cubed amplitude. So despite the fact that we don't directly know some string background that gives us this guy, at least there's not immediately dead as a physical theory, interpreting it as a physical theory. You'll see why I'm making this point in a moment, because we're going to start seeing that maybe it's not crazy to interpret this as an actual physical theory.
Excuse me, Nima.
Yes.
Can I just check with you whether there is an almost stringy background for this?
Yes, there's an almost one. The one where you tune to the self-dual points. Is that what you're going to talk about?
Oh, not really. I was wondering if I can start with vertex operators with the usual Kac-Moody current that we know from the heterotic string,
right,
and then I manually discard all double traces because the double traces are not
good.
Like
I think what happens, I believe, well, maybe we can talk about this later. I think if you manually discard them, isn't it the case that that you get a U-channel pole that doesn't have the positive residue? Maybe.
I thought the pole structure should be all right with a given trace, say trace 1, 2, 3, 4. The single trace, single trace Park-Taylor gives S channel and T channel, not U channel.
Right.
Okay, let's discuss later. I don't want to take away.
Okay, sorry. But anyway, it's still true that that's not some actual known string background, right? You know, we don't know how to make sense of it at loop level. Anyway, but let's maybe talk about let's talk about it afterwards. I just wanted to say that it's not the Kobe-Nielsen amplitude, which was for a tachyon, for example, and it's importantly different. All right, so let's now move on to the stringy forms for our example. Now at one loop. Okay, now we're going to do exactly the same thing. We're going to parameterize the U variables with these Y's. I just showed you how to do it. Okay, up here, it's all the U variables, parameterized in terms of these Y's. And we just do the same thing. Now we have different kinds of variable. We have the XIJs that include the loop variables, the XIIs. Okay, so they're all here. And then we have the U's that correspond to the tagged and the untagged, the plus and the minus spiraling arcs. And I've already told you that these satisfy U equations. So again, as a tree level, this integrand perfectly reflects the factorization of the surface at finite alpha prime. That's a very magical fact. It was magical at tree level. It's doing it at loop level. So let's integrate it and see what we get. Right. So we're going to integrate over the loop momenta and see what we get.
Sorry, Nima.
Yes.
By factorization, you mean also like it gives you the full limit of tree?
Yes, yes.
Which,
but
which
I
is
mean I mean factorization in the general sense. Every limit, forward, pinching, everything. Right. Exactly.
Yeah, at finite alpha prime, this will give you the chi string amplitude you just talked about, right?
Exactly. Yes, exactly.
N plus 2 point.
Yes.
Okay.
Yes, exactly. Yes.
Thanks.
All the stuff you'd expect from the surface, you would get the thing factorizing. But I should have said this. I mean, I don't want to keep saying factorization / opening / pinching. I'm just using factorization.
That I understand. Yeah. But it's slightly different from the type D case where you remove a node from thinking diagram and so on. But still you get like the chi string amplitude, type A string amplitude literally.
Yes,
right?
absolutely.
Okay.
Absolutely. Okay. Because that's what happens at the level of the surface. That's the point, right? At the what you get is exactly what you get at the level of the surface. The U equations that you get when you put some U's to 0 and the other ones to 1 just go to the U equation you had for the underlying surface.
Despite the combinatorics differ from Dn, it has.
Yes, that's right.
Okay.
Yeah.
Great.
Great. Yeah. Okay. So let's do a first comparison with so this is some integral over something that looks like a geometry, a binary geometry. Let's do a very first comparison with what we expect in string theory, even just degree of freedom counting, because I've been drawing the pictures for you as if there was a puncture here, and triangulating the surface with a puncture and so on. So you might think, is what we're doing like a string theory integral here? With the with some worldsheet moduli space anyway with a puncture inside, and it isn't, because this integral, this moduli space is n-1 dimensional. Okay, so when you mod up by SL2, you can use the 2 of the degrees of freedom to shove this guy to the origin and 1 more to fix one guy on the outside. So it's n-1 dimensional, whereas our integral is n dimensional. So what that means is that despite the fact that from the perspective of the triangulations, of the combinatorics and everything, we've been drawing this puncture in the middle as a puncture, really what it is a little hole. It's a little hole with some radius that we're somehow taking into account and integrating over in our binary way of thinking about things. Okay, but that's good. That means that what we're doing is really the annulus diagram would correspond to the annulus diagram in string theory, which is what it should do. We're doing a sort of a one loop open string computation. It should correspond to the annulus diagram, not this one, which corresponds to having a closed string emission. I'll come back to this point in a moment. Okay, but anyway, that's just the very first comparison. All right, so let's look at the very simplest case, the simplest stringy one loop example. And so that's just D1 hat, okay? So D1 hat is just a tadpole diagram, a stupid tadpole diagram. The canonical form is just 1 over y plus 1 over y, 1 over y plus 1 over y minus, right? Here it is 1 over y plus 1 over y tagged. And now when we want to identify these guys with loop momenta, I'm going to write both, I'm going to identify them. You see, at the level of the form, I don't want to identify these things. I don't want to identify the x's going this way and that way. But when I'm integrating, now I want to identify them. So I'm going to put both of them equal to L squared. Plus, for fun, I'll say that these this loop has some mass m. So I'll put these guys to L squared plus m squared. Okay, so this is the canonical form, 1 over L squared plus m squared, or maybe 2 over L squared plus m squared. And then if in the field theory limit I integrated, of course, it's ultraviolet divergent. Okay, so that's our first example of this stupid tadpole whose field theory limit integral is ultraviolet divergent. Okay, let's do the stringy canonical form. Of course, it's just the beta function in this case, right? So we're very, very familiar with it. Now I put y equals y tagged as L squared plus m squared. And now I integrate over L. And I can do the integral over L because it's a Gaussian integral. And I'm left with this amusing looking object. Okay, so it's an integral from 0 to 1 du over 1 minus u. It's an integral over this binary geometry, but now with a more interesting dependence. So we have these familiar factors from the beta function, but we have these interesting log in this case as well, right? And I'm not going to do any analysis on the kind of functions that come out of this, what it looks like yet. I'm just, I only have time here to just show you what just the form of these integrals looks like and tell you a few qualitative things about them. In any case, I don't know that much about what the actual functional form looks like. But already here we can see it's manifestly UV finite. And if you want to have some sense of how it behaves at high energies, you can take this m in the loop and make it larger and larger. There's no kinematic variable, so you can make m larger and larger, and then manifestly it decreases exponentially when m squared is much bigger than 1. Okay, so that's some qualitative thing. Okay, now we can do the general one loop stringy integral, and in the general integral we can put xij equal xji equals xi minus xj squared, and again, except for the adjacent x's. And for the adjacent x's, what do I want to call them? These I plus 1 x's I told you are these propagators on these lines here. And here already there is something kind of cool, which is that even if you're a field theorist, you'd say, well, okay, well, that's some mass renormalization. Do you put some sort of m squared there? Okay, so, but I'm sort of free to do that here. I'm free to give a label to associate with that propagator, and so I'm going to call this guy m squared. And obviously, I'll set them all equal to each other for all of the legs, right? And finally, the xii's, which are these tadpole variables, these might bug you even more because there's a vanishing momentum there. But once again, I'm just going to give it a name. So this is my way of sort of controlling these infrared divergences, these stupid 1 over 0 like infrared divergences that you would associate with these emissions. I'm going to give this guy a name. I'm going to call all of these capital T. Okay. And finally, I will identify the propagators by identifying the plus and the minus variables. I can either write them as loop plus p squared, or in sort of dual variables as x naught minus xi squared. It doesn't matter. But I'm going to integrate over this point x naught. Okay, and after doing that, this is what I get. So this is the form, and don't be frightened. It has the same sort of basic structure we saw before. There are these various pieces that have to do. This is the usual sort of kinematic variables. Here's the dependence on the bubble mass squared on the tadpole. I even put a mass squared for the internal loop variable, the capital M squared here, just so we see all the sort of possible dependence you could have. And then there's a part that comes from the Gaussian integral. And the sort of interesting thing about this is that here we have the dependence on the kinematic variables xij, and then inside we have a more interesting quadratic thing from doing the Gaussian integral, which involves things that look like log over log inside this exponential. All right. But if we just look at the sort of qualitative structure, the tree amplitude is an n-3 dimensional integral of some polynomials u to the power to constant power. So polynomial is u to the alpha prime x. And this is why as alpha prime goes to 0, these things end up being rational. Whereas what we have at one loop now is an n-dimensional integral of some polynomials raised to powers, but also polynomials raised to powers that vary logarithmically, okay? And so it's this piece which lets us, for example, get power or logarithmic divergences as alpha prime goes to 0, and even logs and polylogs as alpha prime goes to 0 is all coming from the behavior of this piece as U approaches its boundaries. Okay. Now, we keep saying that this kind of looks like it may be related to string integrals in some way at one loop, but anyone who knows about string integrals knows they look absolutely nothing like this. Okay, so on the face of it, it does not at all look. We don't see anything periodic. We don't see any theta functions. We don't see anything like that. Any Dedekind etas. We don't see anything like that. We see these slightly, unfamiliar looking integrals, but just with polynomial dependence on the variables and these interesting u to the log u type dependence. Just so you see very explicitly what it looks like in the case of 4-point scattering. This is the whole thing, okay? And again, it has this exponential dependence on s and t, depends on all the rest of the variables, where all of the rows that show up here are explicitly given in terms of those polynomials that are associated with the simplices. So I've just written them all down here, but all of these things are polynomials. All of these guys are polynomials in the y variables. Okay, now, as I said, this doesn't look like at all, on the face of it, doesn't look like a standard one loop string amplitude. So how can we explore it? First of all, is it related to string theory? But even forget that. Secondly, what does it actually do? I mean, we know for a fact that it certainly just gives a UV regularization of our integral. So at the very least, it's some kind of regulated version, UV regulated version of our field theory limit amplitudes. And that's completely obvious. But of course, we're curious. What does it look like when you go to high energies compared to alpha prime? You know, if it was stringy, the stringy amplitudes to have characteristic things, they have Reggie behavior, which you sort of rather trivially see that these guys have. Stringy amplitudes, even going all the way back to a tree level, of course, here they have the feature as these xij's become large and positive, the amplitude becomes manifestly exponentially small. Okay, and that's equally true for us, okay, because these u's are between 0 and 1. So it's manifestly true for us too that in this limit, and that was even true before that was even true at the level of the canonical form before we did the loop integration, but it's also true afterwards. In this limit where all these things become large, these things just become exponentially small. Okay, so the same limit where it's obvious that the tree amplitudes are exponentially small is the limit where the loop amplitude is exponentially small. However, what really gets you excited about string amplitudes, even at tree level, going back to tree level here, is that this is not the physical limit of high energy scattering. This is the kind of unphysical limit where S and T are both large and negative. That's a limit where string amplitudes are sort of trivially soft. What's kind of magical is that in the physical regime where S is large and positive and T is large and negative, but with the ratio of T over S such that it's physical scattering, so that T over S is less than 1, the magnitude is less than 1. In that region, also, the amplitude is exponentially soft. And it's very cool that if you make S very large, T negative, but T more negative than S, so that T over S in magnitude is bigger than 1, then the string amplitude actually grows exponentially. Okay, so it only dies exponentially, first in this very unphysical region where S and T are both negative, but when S is positive, it only dies exponentially in the physical region and actually blows up exponentially in the unphysical region. Okay, so that's something that we could hope to explore here to see, can we understand what this looks like at loop level? And of course, these integrals, just as at tree level, are only well defined as integrals in precisely this unphysical region, where in the way of normalized things now, the unphysical region would be where S and T are both large and positive. I apologize, it's the opposite of the sort of usual East Coast metric convention for a physicist, but anyway. So this is manifestly exponentially soft when S and T are positive, but we want to understand what it looks like when S is very negative, T is positive, but T over S in magnitude is less than 1. Of course, formally, we have to do some analytic continuation of this. I have no idea how to do that at general S&T. But what we normally do is just do a saddle point analysis. Okay. And we're especially interested in this question of what happens in the physical region of high energy fixed angle scattering. Now, at tree level, we know how this works. So the tree level analysis is just the scattering equations written in the language of the U variables. The action that you're looking for an extremum of is just the sum over the kinematic variables xij log uij, and then you just differentiate with respect to all of these y's and look for a critical point. And we know there's n-3 factorial solutions. For example, at 4 points, there's only one saddle, and very, very beautifully, in the high energy fixed angle region, that saddle has negative action. I believe it's the case, but I'm not sure, and someone in the audience might know that always all the n-3 factorial solutions for general n, when you're in the physical Lorentzian region of high energy scattering, all have negative action, which means that even though you don't know which saddle dominates, it doesn't matter for the argument that the amplitude is exponentially small. Whatever saddle dominates, it'll be exponentially small, so long as all the saddles have negative action. If some of the saddles had positive action, you'd have a lot more work to do. You'd have to argue whether or not you access that saddle, etc. But if all the saddles have negative action, you don't have to do that work. Okay, so we would like to do the saddle point analysis for this integral, okay? And at first it looks a little bit more scary because of these exponentials here and so on, but I won't go through the details or even for the general loop integral, but actually it turns out that the saddle point analysis is essentially just as easy as it is at tree level. And it's associated with the following new quote unquote scattering equation, which looks essentially identical to the old one, okay? We still have the sum over just the kinematic variables, because these are the only things that are becoming large. Just the kinematic variables, xij log uij. But now we have to get these uij's from the dn hat surface, from the dn hat variables, rather than, of course, from an that we don't have. So how do you get a uij from the dn hat variables? Well, it's just, there's a uij and a uji, you just take the product. Okay? So this turns out to be the action whose saddles determine the large X behavior of these one loop stringy integrals. Okay? So for instance, there's a 4.1 loop saddle at 4 point. This is the expression, just a concrete expression. Here is u13, here's u24. It's a function of 4 variables. So when you solve these equations, these 4 equations, at tree level, we have one solution. Here, for this one loop case, we have 3 solutions, but amazingly, in the high energy fixed angle region, all 3 have negative action. And so that means the amplitude is exponentially suppressed in the physical region. And just as at tree level, it's not true if we go outside the physical region. If we make S very negative, T very positive, but T over S bigger than 1, some of the saddles have positive action. Okay. But when we're in the physical region, all the saddles have negative action. So I find this very exciting, that this is some indication that all the qualitative properties of this new amplitude look like string amplitudes, even though the sort of form of the integrand and how we're representing it definitely doesn't seem to match up with string theory in an obvious way. So let's think a little bit more of what the sort of relationships between these 2 pictures are, because they don't quite match up with some qualitative points. Although I think we can say a few things about them. So, for instance, if we take the analyst diagram in string theory, there is an infrared divergence in this diagram that corresponds to the emission of a closed string. Okay. Of course, this also only makes sense in 26 or 10 dimensions, blah, blah, blah. But apart from that, there's a sort of qualitative fact that there's an IR divergence here. No such thing occurs here. Notice this is not what I mentioned at the very beginning of the story, that we think of these deltas somehow as associated with gravity. These closed loops associated with gravity. We don't have a delta in this problem. So there's nothing here that appears like it has that kind of pull. But it's definitely true that there are infrared divergences in this picture that would be associated with these tadpoles. Okay, it's just that we in this model, in our model, we get to introduce a parameter t that cuts off that divergence and gives us something finite. String theory doesn't have these parameters that you can add from the outside to control the tadpoles and the bubbles. Our model, whatever it is, does. And so, so while we don't quite see this closed string emission, there is an IR divergence here associated with the tadpole emission, which would be there if we set this t to 0, but which we can control by keeping t finite. Okay, so that's one. And we also, of course, do start seeing the closed strings, and I'll say just one example in a second, involving delta. Once we have not just an annulus, but we have a marked point on this inside annulus, where we get exactly the sort of factorization that we talked about before that corresponds to sort of a pole associated with this variable delta. So we do have this sort of phenomenon of the closed string emission, but it doesn't start with this diagram. It starts with one where we have an extra marked point on the inside. And finally, you could just ask, why is it so hard to compare these two things to each other? I mean, in both cases, we have a two-dimensional integral. There's a two-dimensional moduli space. Why is it that we can't just directly compare? And the reason is that both integrals are somehow an integral over the same two-dimensional moduli space, but the attitude, the way that we are parametrizing the moduli space is radically different than the way the usual string worldsheet picture parametrizes the moduli space. This moduli space of the usual string worldsheet is associated with two numbers, which are the length r here, the size of this little inner annulus you can think of, and the distance between these two marked points. Or if you think in terms of the rectangle model for the annulus, just the sort of side lengths of the rectangle that we're identifying to make the annulus, okay? And this comes from the fact that ultimately in the worldsheet, you have local access to the metric. You sort of imagine you have the surface with a metric on it up to Weil rescaling. But to begin with, there's a z and a z bar in your problem. I mean, you have you're talking about points on the surface, and that's how you're thinking about the moduli space. Whereas this setup, the setup we're talking about, the variables that we like are these geodesic lengths. These y's in this binary setting are really thought of as sort of geodesic lengths on this hyperbolic surface. So it's like a more global way of accessing the metric. It's not like we're looking at sort of individual points on the surface, but by knowledge of what these, what the geodesics look like, you can reconstruct what the metric looks like. So there's some kind of non-trivial mapping between these two variables, even in this very special case. While we in principle know the equations to set up to find the mapping, at least we don't at the moment know exactly what the mapping is between them. If we knew what the mapping was between them, then we would be able to see whether this sort of complicated map might map our relatively simple integrand in y1 and y2 into something that looks more like the stringy integrand in terms of r and theta. But anyway, that's why we can't just sort of directly look and compare the two of them. The pictures we have of the moduli space are sort of qualitatively, they come from qualitatively different starting. So before we transition back to n equals 4 superyoung mills, I want to finish the story that I was just talking about by doing one more example. And this is the first interesting non-planar example, the first example where we encounter delta, and the first example where we have to deal with the infinity, all of that stuff that we've talked about, which is this, this A11 example, where this is the surface, here's a triangulation, and the corresponding diagram are just these bubbles. Okay, just as one bubble. In this picture, all the other triangulations are what you get from this guy by just twisting, and here it corresponds to the integrand by different integrands that you get by shifting the loop momentum by, let's say, the momentum of the internal guy. Okay, so that's the infinitely many copies that we were talking about before that sort of naturally forced on us in this picture. Okay, so let's think about how we talk about this space. And first, if we just imagine now the length variables or the cluster variables associated with this surface, there is this famous quantity by now, even for us, which is invariant. It's like x0 squared plus x1 squared plus 1 over x0 x1, and that's actually equal in all. No matter how much you want. Okay, so that's our favorite delta quantity. It's independent of J. And so that means that because this expression, if I multiply by xj plus 1 and bring it on the other side, is some quadratic expression in xj and xj plus 1 for fixed delta. That means that all the cluster variables, when delta is fixed, all the cluster variables lie on some hyperbola. And of course, every time there's a hyperbola, you should find variables where you write it as xy equals 1, and then you write x, or as xy equals rho squared, and then you write x equals rho e to the t, and y equals rho e to the minus t. Okay, so that's always what we do with the hyperbola. And if we do that in this hyperbola, then we're going to trade these variables, x0 and x1, for two new variables, which I'll call little delta and t. I'll just identify them in a second. But you're supposed to think about this little delta as just telling you the magnitude of capital delta. So it's telling you which one of these hyperbolas you're on. And this little t is just moving you around the hyperbola, okay? And here's what the explicit variables end up being. So if I write capital delta as e to the little delta plus e to the negative little delta, and these are the xj's, it's cosh of t plus j delta over stinch delta, then yeah, that's the parameterization. Okay? That's the parameterization of all the cluster variables now as a function of little t and delta instead of as a function of x0 and x1, which is what you would start off doing it as. Notice that in this way of writing it, the action of the mapping class group, which is just translating j by 1, is really simple. It's just translating t. T goes to t plus delta. And another lovely thing is that the sort of, canonical form on the initial cluster variables is even simpler in terms of the t and delta variables. It's just dt, d delta. These are the Fenchel-Nielsen coordinates for the surface in this case. I don't know what that means, but I'm told that that's what they are. Okay? So, all right. Now, having done this, let's go and see if we can define U variables for this problem. Now, in general, defining U variable, there's various ways of thinking about it. There's a way that makes sense in finite type, where you start from some acyclic quiver and you walk. If you don't know what this means, it doesn't matter. What I'm going to say is self-contained anyway. But this A11 example is so simple that there's essentially only one reasonable way of defining the U's, and this is it. Okay, that the U's is defined as this ratio, xj squared over xj of the guys separated by 2, and the one in the middle is squared. It's sort of totally conventional why I chose to put the j here rather than somewhere else, but anyway, that's the way I chose to do it. And so these UJs explicitly are given by this cosh squared over cosh type expression. And so those are the UJs. Now, since we're sort of interested in U plus U equals 1 equations, the first thing to do is just see what the product of all these U's looks like. And it's a sort of very simple exercise. There's a telescopic cancellation here, but as you go out to infinity, there's something that doesn't cancel, and asymptotically, it approaches e to the minus 2 delta. Okay, so that's kind of a nice thing, that this infinite product of the U's is equal to e to the minus 2 delta. And then by similar telescopic cancellation of numerator and denominator, you can verify the following equation, which I've written for U naught, but because everything here is manifestly translational invariant in J, it's true for all the rest of them, which is that U naught plus U1, U minus 1, U2 squared, U minus 2 squared, U3 squared, U minus 3 squared, etc. That's what the naive U equations would be. These powers 2, 3, 4 are just the intersection numbers, right? U naught doesn't go wind at all, so U1 intersects once, U2 intersects twice, U3 intersects 3 times, and so on. So these are the naive intersection numbers. You can compute this big product, but you find that the formula is not correct, that U naught plus the product of all these guys is equal to 1. But it becomes correct if you multiply this product by 1 minus e to the negative 2 delta all squared. So that's interesting. That motivates us to define this object, 1 minus e to the minus 2 delta. It motivates us to call that U sub delta. Okay, so we're going to call that U sub delta. And then when we do that, something beautiful happens. So first we have Uj plus the product of all of these guys of the appropriate intersection numbers. U delta squared is equal to 1. And then I just told you that the product of all the U's was e to the minus delta. So if I bring it to the right-hand side, well, that's exactly what U delta is. Okay, so we get the remaining U equations that says that delta is incompatible with all of the rest of them. Okay, so these are the binary equations for A11. There's these infinite equations. We need this extra U delta, otherwise it wouldn't work. And they're just solved. Here's the solution. I've just written again that this is a solution for Uj and U delta in terms of little delta and T. Again, U delta doesn't depend on T. Okay. So we have these explicit U variables that satisfy these binary equations. And it's quite beautiful that this binary geometry also asks for delta. So we've seen that a number of times already. We saw that we needed the delta because there's that missing piece of the fan. We saw that we need the delta, otherwise the polytope doesn't close. Now we see that we need the delta because otherwise we don't get binary equations. Okay. All right, but now we can do the string integral. Okay, and what should we do? Remember, all of these xj's are the same damn propagator. We're just shifting what I mean by the loop momentum. So all these xj's are just L squared plus M squared, where I shift L goes to L plus PJ. Okay, so xj is L plus PJ squared plus M squared. And so if I write down the stringy canonical form, here it is. Okay, now remember the integral over the measure is now d delta dt. Delta goes from 0 to infinity, t from minus infinity to infinity. And then I have a product over j, uj to the alpha prime xj. Okay, so, oh, sorry, and I should have written down maybe a u delta to the x delta. I forgot to write that down. There's also a u delta to the x delta here. But in any case, this by construction is something whose alpha prime goes to zero limit will give us the infinite form that we were talking about. The infinite form associated with this infinite polygon. And therefore, if we were to integrate it, in other words, if we imagine we did this integral first, and then we integrated over loop momenta, we're clearly going to get infinity times the amplitude by the dumb reason that we're counting the diagrams infinitely often. So let's not do that. Let's do the loop integral first, just as we were doing in our previous examples, right? That's the whole idea here is we're doing the loop integral first. So, and there's just the following trivial point. When we do the loop integral first, we leave this dt d delta thing left, and after we do the loop integral, we're going to have some function that's left that's a function of little t and delta. Now, the point is that the integrand under a mapping class group was invariant only if you shift L. So after shift L goes to L plus P. So that's why the integrand is sort of covariant under the action of the mapping class group, and that's why we have to have this infinite copies business. Okay. But after I do the integral over L is gone. And so this function that's left over is just invariant under the mapping class group, okay? So this guy is just invariant. F of t plus delta is just equal to f of t. If I write this little t as delta times tau, it's just that tau goes to tau plus 1, all right? And so that's why this integral is infinitely too big for the stupid reason that this thing is just invariant under tau goes to tau plus 1, but I'm integrating over all tau. But this is the standard thing that we deal with all the time when we do worldsheet integrals or even much more trivial things. Here we should just integrate over a fundamental domain and not to overcount. I just want to do this tau integral over a region of size 1. And then if I do that, I've solved my infinite overcounting problem. Okay? So that's it. So I will choose to do this integral over t between, let's say, minus delta half to delta half. The rest of the integral from 0 to infinity of this function f of t and delta. And this is now manifestly, even at finite alpha prime, it's a finite amplitude, the infinite overcounting problem is gone. And this is going to be a general point if we manage to find binary geometries or some version of that for general surfaces. We don't know how to do it for general surfaces. We know how to do it for AN and DN hats and these annuli. We'd like to know how to do it for general surfaces. But if we could do it for general surfaces, this is always going to be the phenomenon. When you do the loop integral first, you're going to be left with an integral over the whole space, which is now invariant under the mapping class group. And at that point, you mod out by the mapping class group and you're done. The infinite overcounting problem is gone without any manual monkeying with the notion of a fundamental domain at the level of the integrand. Okay? Here, finding the notion of the fundamental domain ends up being where it should be at the level of the integral over the whole moduli space instead. But in any case, in this concrete example, that's just what happens. And this is what you actually get. So when you do the integral over L, it's like some of our previous examples. that we saw. So we have these kind of factors here. I've included the u to the delta factor. And now from the Gaussian integral over the loop momentum, you get the following kind of cool expression. The sum over j and k, j minus k squared log uj log uk. This looks like a kind of a complicated expression, maybe. Each one of these uj's is a log cosh, right? Sorry, each one of these uj's is a cosh. So I'm supposed to take log of this expression and sum and so on. I don't know how to do this. We don't know how to do this analytically, but observationally, it looks like this collapses to an extremely simple expression, which is a constant plus something quadratic in tau times delta squared. At least numerically, when you evaluate this, it's exactly of this form. And you can actually guess this form by looking at the asymptotics, both as delta goes to 0 and delta goes to infinity. In the asymptotic limits, it's easy to see that you get a constant here and you get this behavior as delta goes to infinity. You can do that with a little bit of work. So you might naively just add them together. And when you add them together and just compare what this looks like numerically to this thing, it's extremely close. So maybe they might even be identical. Anyway, I'm not sure if they're identical or not, but it's an extremely good approximation if not. So we get an integral that looks like this, whose dependence on delta looks like that. And now it's really easy. Now we do the integral over tau, which is a simple thing. If I want to do it analytically, I'd get a best. But I'm not going to do it. I'm just going to leave it like that. So the final integral looks like these factors, and then at least to an extremely good approximation, if not exactly, a factor that looks like that. And now you can do various experiments with this. For example, in d equals 4, in 4 space-time dimensions, just for fun, if I set this x delta to 0 and just ask what happens as the p squared goes to 0 here, or then you can see that this integral develops a logarithmic divergence. And it looks like log alpha prime p squared. That's exactly what this bubble integral should look like, but it's cut off. It's cut off in the uv by alpha prime, again, as it should be. In general dimensions, if instead you send p squared to 0 first, but you keep this x delta, this delta variable, remember in this case, the delta variable is supposed to look like the closed string. If I just set x delta to a constant, then remarkably, you find this expression has an infinite sequence of poles at p squared minus n minus d half over 2 for n equals 0, 1, 2, 3, 4, etc. So this looks like an infinite sequence of quote unquote closed string poles that you would associate with this delta variable, not just the field theory limit, but a sequence of poles associated, a whole infinite sequence of poles. And quite amusingly, when d equals 4, there's a massless quote unquote graviton associated with this delta in 4 dimensions. Okay, so if you put d equals 4 in this formula, there's actually a pole that starts off at 1 over p squared. Okay, so those are the 2 examples that I wanted to talk about for what these stringy integrals look like at one loop for the general planar case, and the simplest case of the annulus, where we see that this stringy way of thinking about the integral lets us have our perfect infinite polytope, in this case, our perfect infinite polygon with this perfect canonical form. We don't have to do anything to it. We don't have to mutilate it in any way. We just do the loop integral, and then we mod out by the mapping class group, and we get a finite object. Okay, so one can hope that that idea will carry forth in general if we manage to find the binary geometries, or whatever the appropriate notion should be that hopefully generalizes it if we can't directly find binary geometries for general surfaces. All right, so that's all I wanted to say about the string integrals. Again, if people are interested in the dual surfacehedron representation of the integrals, I'm happy to talk about that in discussion. But maybe I'll stop here and ask for questions, and then move on to the story of the amplituhedron and go into strong couple. Any questions?
Nima.
Yeah.
When you do the saddle point for the one loop case, you only keep S and T. All other exponents are not your
No,
kinematic.
because I'm imagining just because you see, I'm only using those other things to regulate the IR emission of the tadpoles and the bubbles. So I'm keeping them all finite, but going to high energy. So that's why it makes sense to do that.
So you just have
yeah.
The same kinematic as a tree level, right? You're just
exactly
multiplying
that's the point. So,
Uij,
yeah.
Uji. Okay.
Exactly. Yeah. So that's why. So the maybe slightly surprising thing, you see, before I do the loop integrals, if you ask how would you take the saddle point, that's what you do, because that's where they show up, right? The other ones, that's where the kinematic variables show up, and then the other ones have the loops in them. But of course, after you do the loop integrals, you also get the kinematics showing up in that exponent. So that's why at first it looks maybe hard, but you can do some manipulations on that exponent to clean things up a little, and then when you take the high energy limit, it turns out that really the naive thing was actually correct, that the saddle point is really given by just what you got from that tree part there. And I should say that's sort of generally encouraging, because in the stringy way of doing this, a la Gross-Mende, that's something that they find, is that even though you have sort of complicated surfaces, that it's the same scattering equation that shows up for more and more complicated surfaces. So that means that there should be some kind of relationship between the loop surface, the loop saddle, and the tree saddle. And here we see there's some kind of relationship between the loop saddle and the tree saddle. We start from the loop U's and we build things that look like the tree U's. You can ask you might have asked the following question, Song, probably the next question that you would ask. These capital U variables that I defined, that are the product of the Uij and the Uji, do they satisfy capital U equations? And the answer is they satisfy something slightly better. I mean, slightly more extreme. They satisfy capital U plus capital U is bigger than 1, strictly bigger than 1. And that also gives you a binary geometry. It gives you a binary geometry because when U goes to 0, the product of the capital U's has got to be bigger than 1, but you secretly know otherwise that the U's are less than 1, so they have to all equal 1.
Sure.
Okay. So so they don't satisfy literally the same U equations, but so it's U plus U is bigger than the 1. And I think these are we haven't done any analysis on the analog of n-3 factorial, how many solutions there are, none of that. But anyway, I think it's slightly encouraging that we see a kind of a similar sort of structure, even in the one loop case, as far as the saddle point analysis goes. That would sort of, I think, have to be the case if it's going to match up with the Gross-Mende picture in some way. But anyway, the investigations are all very, very primitive. So I really have no idea what the chances are that this is really some rewriting of the standard string worldsheet sort of integrals. I mean, part of the problem is that it's not, I mean, some things just don't seem to match. Like string theory does not have the freedom.
Sorry, I mean, what if you take alpha prime to 0? Like, do you recover some?
Alpha prime goes 0, we get field theory limit. We get field theory limit with the ultraviolet divergences cut off by alpha prime. So we can't take alpha prime all the way to 0 because there's UV divergences, but we get a field theory limit with all the divergences cut off by alpha prime.
But at the level of the loop integrand, for a fixed L, doing an alpha prime expansion, as a function of L. Have you tried this for some subleading orders, perhaps?
Oh, sorry. At the level of the loop integrand, but it's manifest that as alpha prime goes to 0, we get the field theory limit. And now you could ask what we get in the alpha prime expansion. That's something that you remember, Oliver, we talked about when you were visiting Harvard, when we were talking with Song, that we might want to try that on the DN integrands that we were talking about back then, which are sort of close to this. By the way, I should say, what's the relationship between this and the DN polytope? The reason we couldn't do this with the DN polytope is exactly this business about how we treat the tag variables. Because in the DN polytope, what we want to do is set the Y and the Y tags equal to each other, and then do the integral. The problem is if we do that, the quote unquote tadpole diagrams really have double propagators, and they don't have the correct field theory limit. Okay, so it's not the correct field theory limit to do that. That's why this DN hat sort of solves that problem. We get explicit tadpole variable, and then we just get 2 copies on both sides, but now it makes sense. But apart from that, they're similar. But that was enough of an obstruction to show that you would not get the same answer if you integrate as the correct field theory answer of the dn. But it could be that that if we look at the alpha prime expansion of the integrand, that might give you a clue for how it connects to things that you know about what the integrand looks like. I guess one question for you or anyone else is, are the loop integrands sort of available in this? I mean, these aren't linear propagators or anything. These are just good old-fashioned honest propagators. So do you have access to the loop integrand in terms of the good old-fashioned honest propagators, or only in terms of things that have linear propagators?
Yeah, we have something in preparation with colleagues in Uppsala, which is very much tailored to the supersymmetric setup. Say where the Park-Taylors you stick into the integrand are sufficiently symmetrized that you're not bothered by tadpole or bubble problems, at least at low orders in alpha prime.
Okay.
Yeah.
All right.
We'll try to send you a
in that case, I think trying to do the alpha prime expansion of these stringy canonical integrals, that's much closer to standard stuff, right? I mean, that because it looks just like a stringy integral, and whatever you do with the tree amplitude and string theory, it's very similar things here. And we would expect you just see zeta. You don't see any fancier numbers coming out of it than the numbers that we expect. So so that's, I think, that's a kind of a clear thing to try and do. Anyway, but in sort of fantasizing, there might be a real physical model here or a real physical connection to string theory. Trying to take the opposite limit of looking at the amplitude and just see what the actual properties look like is something else that you can do, and I think it's encouraging that it has so many of the qualitative properties in common.
Nima, can I ask a question?
Yes.
Hi.
Hey, James, how you doing, man?
Hi. Good to see you. So, am I right in that you're sort of making this model? It's a sort of model for the massless modes in this stringy theory. Is there anything that might be natural that you would allow you to include massive modes on the outside?
I think you mean, I mean, of course, you discover, quote unquote, discover the massive modes in the poles.
Right, right. But you would like to.
From this point of view, why you would think you're supposed to invent complicated vertex operators that make the states and so on, I have no idea why you'd think to do that. So yeah, I don't have a good answer to that question yet. I have a kind of a lame excuse though, which you may or may not like. I don't like, so you probably won't like, but which is that ultimately the only states that really are there in this theory are the massless modes. All the other ones decay. So the actual S matrix is only an S matrix for the massless modes. And so anyway, that's a lame excuse, but yeah. So anyway, there's a few qualitative tensions here, right? That both of these things are integrals over the same moduli space, okay? But they have very different attitudes about how they think about the moduli space, either locally in terms of the metric up to Wylby scaling, or globally in terms of the length of geodesics. That's why it's hard to compare the two of them directly. But the fact that at tree level it's the same, and the integrands are the same, I mean, it's hard to believe they can be so similar at that level and not be the same. So that's the direction where you think it's the same. But if they are the same, what the hell is this thing that we're doing? Because there is no string theory with stupid scalars, non-supersymmetric, where you get to add by hand these tadpole variables and bubble variables. I mean, those things are perfectly natural from the mathematics of the objects we're talking about, but they don't exist in the physics. That's, the tadpole is generated and you make a runaway potential and the thing runs away, right? So that's what I don't understand. Those are the countervailing tensions here. That something looks clearly stringy, but if it is stringy, there isn't some like actual string theory you can point to and say, aha, it's that one. I mean, maybe maybe the sort of supersymmetrization of the whole thing will end up looking natural from some, I don't know, from some perspective that we don't see yet. And maybe if we do that and we keep going down this line, maybe it's like we want to somehow eliminate the dependence on these B's and T's, and then we have to decorate all this with something that ends up giving us the supersymmetric version of this crazy way of thinking about the moduli space. That's one way of thinking about it. But anyway, that's now getting very, very speculative.
Question.
Yeah, but anyway, but James, but just say I totally agree that what the world sheet perspective and the vertex operator and so on gives you is a very nice understanding of why there's all these other things lying around too, which I definitely don't see in this picture yet.
Hi, can I ask a question?
Hi, Wolfgang. Great to see you.
Hi. So you said the modular space is the same. Well, on tree level, okay, but in one loop, I mean, you had this integral from rho tau from -1/2 to 1/2, which is a straight line over the lower boundary of the fundamental, not fundamental domain. And I always thought the real stringiness is lies in the shape of the fundamental domains. So the numerical integral will be different than in string theory.
You might be right. Yeah, I mean, I'm not. Well, except, I mean, to the extent that we're talking about, to the extent that we have the same space and we're modding up of the same mapping class group, I think it should be the same. Here, I don't see the SL2Z in this example, though. Yeah. So, yeah. But really, I meant something still at this point a little more impressionistic. The dimensions match, the surfaces match. But sort of precisely what we're doing does not look, yeah, I have no idea how close or far it is. But, and yet, just to say, it can't be that field theoretic because we get the correct exponential soft behavior even at one loop. Okay? So it's not something purely field theoretic. We know we don't get that field theoretic behavior. We know we don't get exponential softness in field theory. So.
Thanks.
May I ask a question, Nima?
Yes.
So you showed during the talk, and it was also earlier this week, what the picture of the polytope for D2 hat and D3 hat.
Yes.
I was wondering if there's anything known about what the family of the DN hat polytopes look like.
You mean what about it? I mean, they're explicitly cut out. We know the facet structure. I mean, what is it specifically about it you want to know?
If they had shown up before in the literature.
Well, I don't know if they've shown up before. What I can tell you is that Hugh appears to like them. Are you on the line, Hugh? Maybe he's not on the line. But anyway, yeah, I mean, Hugh likes them from a representation theoretic point of view.
Mm-hmm.
But I don't know if he'd seen them before or that he just likes them. So yeah, I'm not sure.
But you said you do know like the facet structure and the F vectors and
that's right.
Kind of
data.
Well,
I mean, I don't know the F vector. I don't know the F vector. I don't know if it's possible to work out or not. I don't know the F vector. But the facet structure is sorry. When I say the facet structure is understood, I just mean the combinatorics of how it factorizes into lower things is understood.
Yeah.
No. But it's the short answer is I don't know the F vector. Maybe it's possible to work out pretty easily. I mean, it seems about as simple as the Surfacehedra.
Right.
It's really extremely closely related to the Surfacehedra. And if I compare with the DN cluster polytope, something that those of us who played with it with the DN cluster polytope were always slightly frustrated by is that they're like the F polynomials are not, they have interesting terms corresponding to points on the inside of the corresponding Newton polytopes, a little bit complicated. They're not, the Minkowski summands are not just simplices and so on. Whereas here, everything looks just identical to what you see in AN. It's just you take the same guys and you sort of combine them together in a slightly different way. And it's simpler than AN in the sense that it's completely cyclically invariant, unlike AN where you always make a little bit of a choice that it's not cyclically invariant. So it's really, they're, yeah. And we could talk more about about what's going on at the level of the precise relation between dn and dn hat, both at the level of the polytope and the level of the cluster algebra, is very, very simple to describe. I mean, there's not some big dramatic difference, but somehow it's really important. You see, one of the funny things about the whole picture of tagging in cluster algebras is it forces various exceptions very low down. For instance, you don't talk about D1, right? There's no D1. You're not allowed to talk about that one, but in this entire structure that we like, both, I mean, not just for surfaces, but for other amplituhedra, it's very important that even the most degenerate, tiniest cases are sort of connected to the whole story. And it's sort of funny to have exceptions down to the bottom. And this always bugged me a little, even when I didn't know much about the tagging story. You're not allowed to talk about the three-punctured sphere. You're not allowed to talk about these tiny examples. Whereas, you know, we know that the tiniest examples are what everything boils down to in you know, ultimately, when you keep factoring and factoring and factoring, you end up getting to these tiniest things at the bottom. Mm-hmm. So it's for those things that it actually makes a difference. So we have D1 hats. That's perfectly fine because yeah. So that makes sense. And you know, just to say another thing. If you want to imagine that I mean, here's a way of thinking about what the DN hat polytope is. Imagine that you have the polytope where instead of having the puncture, you opened it up into a little circle with a marked point on it, right? Even forget about a polytope. You have a fan associated with that. Well, I mean, it makes sense that you want to project through the sort of delta that goes around that guy. You know this better than I do. And that gives you some fan downstairs if you do that, right? So, well, you would like it that the guys that were, so for instance, you had a perfectly healthy, reasonable variable upstairs, which was the loop that goes around that goes around the inside annulus with a point on it. That's a legal variable upstairs. So it's a little funny that after you project through that, that's no longer a legal variable downstairs. Mm-hmm. Okay, and so that's why we need to keep that guy. And analogously, it's funny that before you project, the things that wind around this way and wind around that way are horribly incompatible, but after you project, you call them compatible. So that's the sense in which the DN story, or more generally, the cluster way of thinking about the tagging is in some tension with what looks natural from the perspective of projecting more complicated surfaces down to simpler ones and so on. So, but at the level of the fans, it's a completely sensible thing to do, because always the fans that contain one tag guy and the loop variable contain the other tag guy in the loop. So it's perfectly reasonable to put those two cones together and call it a new cone. And that's what the cluster fan is doing. So that's why it's perfectly correct. Everything is fine, but it's artificial from the perspective of the surface. Sorry, not artificial, it's unnatural from the perspective of the surface. Yeah. Okay. All right. So shall we start again, Livia?
You're muted, Livia.
Okay. Good.
I am unmuted. This is why
I
said, okay, sorry. I suggested to pass to the second part.
Okay, great.
The talk and postpone the questions. No.
Sorry about that. All right. So, okay. So we're going to switch topics now and talk about how we can at least start on a path to go from the positive geometry of the amplituhedron, think about the amplitudes, take the amplitudes to strong coupling, and somehow begin to see the emergence of empty de Sitter space. And this is work in progress with the two wonderful old friends, Yara, of course, and Johannes, and actually realized in putting this, in just talking about this, that shockingly, Johannes and I have never written a paper together. I was sure we'd written something together because we talk physics so much, but anyway, we've never written a paper together. So anyway, this is hopefully that's going to change when this comes out. All right.